Imagine a sealed room with a single instrument sitting on the floor, the kind that measures acceleration. It reads 1 Earth gravity, exactly what you would expect. Then the cable holding the room snaps, the room begins to fall, and the instrument reads 0. Not a reduced number. 0, and it will keep reading 0 for as long as the fall lasts. That instrument was never measuring the Earth pulling on it. It was measuring the floor pushing back, which means something that sounds impossible and is simply true. You have never felt gravity in your life. You have felt chairs and pavements and the soles of your shoes. But here is what gets left out of that story. If gravity is not a force and nothing is passing between you and the planet, then what exactly is it made of? Physics does have an answer. The thing has a name, a mass, a spin, and a complete specification sheet, written out to 23 decimal places. Nobody has ever seen one. And there is a short, simple argument that says nobody in this universe ever will. Get comfortable. Hit subscribe if you're new here, because by the end of tonight, you will know exactly what gravity is made of, and why that answer arrives, carrying 4 qualifications, every one of them stranger than the sentence itself. Now, let's slowly ease into this. Part 1. The 3 answers and the missing one. There is a question you can ask about any force in nature, and for 3 of the 4 forces the answer is a short, confident sentence. Ask what the electromagnetic force is made of, and the answer is photons. Not a metaphor, not a model, not a useful way of thinking about it. Photons. Particles of light with no mass, carrying 1 unit of spin, produced by the trillion in every fluorescent tube above your head, and counted individually by detectors in laboratories all over the world. When 2 electrons push each other apart, what passes between them is photons. Albert Einstein put the idea on the table in 1905, and Arthur Compton nailed it down in 1923 by bouncing X-rays off electrons and watching them recoil, exactly the way billiard balls do. Ask what the strong nuclear force is made of, the force that holds the nucleus of every atom in your body together, against the enormous electrical repulsion of protons crowded into a space smaller than 1/millionth of a billionth of a meter, and the answer is gluons. 8 of them, massless, spin 1. Nobody has ever isolated a single gluon because the strong force does not permit it. But in 1979, at a collider called Petra in Hamburg, physicists watched electron and positron collisions spray out 3 jets of particles instead of 2, and the 3rd jet was a gluon announcing itself. It has been part of the standard inventory of reality ever since. Ask what the weak nuclear force is made of, the force that lets a neutron turn into a proton and makes the sun burn slowly enough to have a habitable planet underneath it. And the answer is the W and Z bosons. Massive ones, unusually so, around 80 and 90 times the mass of a proton. They were produced at CERN in 1983 by 2 teams working on the super-proton synchrotron, and Carlo Rubbia and Simon van der Meer had Nobel Prizes for it the following year. 3 forces, 3 answers. Each answer is a particle that has been made, detected, weighed, and put into a table. Now ask the 4th question. What is gravity made of? There is an answer to that one too. It has a name. It is called the graviton. And this is where the story stops behaving like the other 3, because the graviton has never been detected. Not once, not indirectly, not in a jet, not as a missing energy signature, not as a recoil. Nobody has ever produced one, counted one, or measured one. And yet, if you sat down with a theoretical physicist and asked them to describe it, they would not hesitate for a second. They would tell you it has exactly 0 mass. They would tell you it carries 2 units of spin. They would tell you it has 2 polarization states, that it couples to absolutely everything with precisely the same strength, and that the force it produces can only ever pull, and can never push. They would be able to tell you why each of those things must be true, and then, if they were being honest with you, they would tell you that the chances of anyone ever holding one in a detector are somewhere close to zero, and not because our instruments are not good enough yet. That combination does not exist anywhere else in physics. The graviton is the most completely described object that nobody has ever seen. So here is the sentence that physics gives you when you ask what gravity is made of. Gravity is made of gravitons. Hold on to that sentence, because we are going to come back to it at the very end of tonight, word for word, and by then it will mean something entirely different from what it means to you right now. At this moment, it probably sounds like a fact being handed over. By the end, it will sound like a fact being handed over with 4 separate qualifications attached to it, and every one of those qualifications is more interesting than the sentence itself. Because the honest situation is stranger than either of the 2 stories you usually get told. The first story you hear is that quantum gravity is an unsolved problem, that physics has no idea how gravity works at the quantum level, that this is the great missing piece and nobody has found it. The second story you hear is that string theory solved it years ago and everyone is just waiting for the experiment. Neither of those is right. What is actually true is more specific and better. There is a working quantum theory of gravity. It has existed since 1994. It makes real, calculable, parameter-free predictions, and the calculations are done with gravitons in exactly the way that calculations in quantum electrodynamics are done with photons. The theory does not fail because it is wrong. It fails because it runs out of validity at an energy so enormous that the failure has, for most of the last century, been treated as though the theory simply did not exist. And underneath all of that sits a much older objection, which is that the question might be badly posed to begin with. Because there is a version of the answer, and it is Einstein's version, in which gravity is not made of anything at all, in which asking what gravity is made of is a little like asking what the equator is made of, or what downhill is made of, or what tomorrow is made of. That is not a dodge. It is the most successful theory of gravity ever written, and it says, quite plainly, that gravity is not a force and there is nothing being exchanged. So there are at least 3 answers layered on top of one another, and they do not agree with each other, and each one is defensible. Gravity is not made of anything, because it is geometry. Gravity is made of gravitons, because every field in nature turns out to be granular when you look closely enough. And gravity is made of something else entirely, strings, or discrete atoms of space, or ordered events, or pure correlation, because the graviton itself might not be fundamental. We are going to go down through all 3 of them tonight, slowly, in order, and we are going to end up somewhere quite specific, not at a shrug, at an answer. But we have to start where Einstein started, which is by taking the question apart. Because before you can ask what gravity is made of, you have to be sure that gravity is the sort of thing that is made of anything at all, and there is a very good argument, more than a century old, that it is not. Part 2. The force that isn't a force. I want you to do something in your head, and I want you to take it slowly, because the conclusion at the end of it is going to feel wrong for a moment before it feels obvious. Imagine you are sitting in a sealed room, no windows, nothing to see outside, nothing to hear outside. On the floor in front of you is a small instrument, an accelerometer, the same kind of device that sits inside your phone and tells it which way up it is. It has a single readout on the front, a number, and right now, that number is showing 1 g. 1 Earth gravity, exactly what you would expect. Now the room begins to fall. The cable snaps, or the floor gives way, or the whole structure is simply released from a great height. It does not matter how. The room is in free fall. Look at the instrument. It reads 0. Not a small number, not a reduced number. 0. and it will keep reading 0 for as long as the fall lasts, whether that is 2 seconds or 2 hours or the rest of your life. The instrument sitting inside a falling room in the gravitational field of a planet detects no gravity at all. Now think about what that instrument was measuring a moment ago, when the room was still standing on the ground. It was not measuring the earth pulling on it. It was measuring the floor pushing on it. The floor, made of atoms, held apart by electromagnetic forces between electron clouds, pressing upward against the underside of the instrument. That push was the entire reading, and the moment the floor went away, the reading went with it. Here is the sentence that comes out of that, and it is one of the strangest true sentences in physics. You have never felt gravity in your life. You have felt a chair. You have felt a mattress, a pavement, a pair of shoes, the deck of a boat. Every sensation you have ever called the feeling of weight has been the sensation of something solid refusing to let you fall, and refusing electromagnetically, atom against atom. In the moments when gravity is the only thing acting on you, jumping from a diving board, riding an aircraft through the top of a parabola, drifting in orbit 250 miles above the ocean, you feel nothing at all. Astronauts on the International Space Station are not beyond Earth's gravity. At that altitude, the Earth pulls on them with about 90% of the strength it pulls on you. They float because they are falling, continuously, and missing. Einstein arrived at that thought in 1907, and he later called it the happiest thought of his life. A person falling freely, he realized, does not feel their own weight. And if the sensation of gravity vanishes simply by letting go, then gravity cannot be a force in the way that a push or a pull is a force. Something has gone badly wrong with the accounting. What he built out of that thought over the following 8 years is general relativity, and the picture it gives is this. Mass and energy bend the geometry of space and time around them. Objects, moving through that bent geometry, follow the straightest path available to them, not a curved path pushed by an invisible hand, but a straight path through something that is no longer flat. The Earth does not pull the Moon. The Earth deforms the shape of space-time in its neighborhood, and the Moon coasts along that shape, going as straight as it is possible to go, and the shape is such that going straight brings it back around. That word straight is doing a lot of work, so let me make it concrete. Take 2 people standing on the equator, several hundred kilometers apart, both facing due north. Both start walking. Neither turns. Neither steers toward the other. Both walk in the straightest line their feet can produce, and they will meet at the North Pole. If those 2 people had no idea they were on a sphere, they would swear that some force had been pulling them together the whole way. There was no force. There was only a curved surface and 2 straight lines on it. Gravity, in Einstein's picture, is that. Except the curved thing is not a surface, it is space and time together, and the straight lines are the paths of everything that exists. There is one detail worth adding, because it is the detail that keeps the geometric picture honest. If the falling room were large enough, the instrument would not read exactly 0 everywhere inside it. 2 objects released at opposite ends of a very tall falling room are both heading toward the center of the Earth, and the center of the Earth is one place, not 2, so their paths very slowly converge. 2 objects released one above the other are at slightly different distances from the center, so the lower one falls slightly faster and they very slowly separate. That squeezing sideways and stretching lengthwise is called tidal force, and it is the one thing about gravity that cannot be made to vanish by falling. It is the true fingerprint of curvature. Everything else you have ever called gravity can be erased by letting go. That cannot. And this is also the part of the theory that has been tested hardest, because if gravity really is nothing but geometry, then every object must fall the same way, regardless of what it is made of. Geometry does not know what material you are. Experiments with torsion balances, most famously the long-running work of the group at the University of Washington, have compared the falling rates of different materials to a precision of a few parts in 10 to the 13. Aluminium and beryllium, titanium and platinum, the Earth's own iron core against its silicate mantle. Nothing has ever come apart. To the limits of measurement, everything falls identically, which is exactly what you would expect if falling is not something being done to objects, but something the objects are simply doing. And this picture is not a philosophical preference. It is the most precisely tested theory of gravity we possess. In 1919, Arthur Eddington's expeditions measured starlight bending around the sun during a total eclipse by roughly 1.75 seconds of arc, and it matched. In 2015, on the 14th of September, two black holes 36 and 29 times the mass of the Sun collided 1.3 billion light-years away, and the ripple in space-time that reached Earth stretched the 4-kilometer arms of the LIGO detectors by about 1 part in 10 to the 21, a distance 1,000 times smaller than the width of a proton, and the waveform matched Einstein's equations beat for beat. Every satellite navigation system on the planet has to correct for the fact that clocks in orbit run faster than clocks on the ground by about 38 microseconds a day. Without that correction, your position would drift by roughly 11 kilometers every day. So general relativity works. And general relativity says gravity is not a force, nothing is being exchanged, and there is no substance involved. Which means that on this reading, the question we started with does not have an answer because it does not have a subject. Asking what gravity is made of would be like asking what the equator is made of. The equator is not made of anything. It is a relationship between places. Asking what downhill is made of, or what a corner is made of, or what a shadow is made of. These are not questions with substances at the end of them. They are questions about shape. For about 15 years after 1915, that was where the matter rested, and a great many physicists thought it was where the matter would stay. Gravity had been explained by removing it. The most successful thing anyone had ever done with the force was to demonstrate that it was not one. And then the rest of physics came along and made the question impossible to leave alone. Because while Einstein was turning gravity into geometry, an entirely separate group of people were discovering something about the nature of every other field in the universe, something that, once you know it, makes the geometric answer feel not wrong exactly, but unfinished. Deferred, a very good way of describing what gravity does, that says nothing whatsoever about what gravity is. What they discovered was that nature does not do smooth. Part 3. Everything in nature comes in pieces. The 20th century has a single sentence at the center of it, and the sentence is this: everything that looked continuous turned out to come in pieces. It began with light, and it began with an embarrassment. At the end of the 1800s, physicists tried to calculate how much energy a hot object should radiate at each color, and the answer their equations gave was infinity. Not a large number, infinity. A glowing coal in a fireplace should, by the mathematics of the time, be pouring out unlimited energy at the blue end of the spectrum, and since it plainly was not, something in the foundations was broken. In the year 1900, Max Planck fixed it with a move he described, later, and with visible discomfort, as an act of desperation. He assumed that the energy could only be emitted in discrete lumps, in whole number multiples of a very small quantity. He did not believe it described reality. He thought it was a mathematical trick that happened to give the right curve. It gave exactly the right curve. 5 years later, Einstein took the trick seriously and used it to explain why shining light on a metal knocks electrons out of it only above a certain color threshold, no matter how bright the light is. If light were a continuous wave, brightness would be everything, and color would be a detail. It is the other way around, because light is delivered in packets, and one packet either has enough energy to free an electron, or it does not. That is the photoelectric effect. It is the discovery that got Einstein his Nobel Prize, not relativity. And it is the moment the pattern started. Once the pattern started, it did not stop. The electron is not a little ball moving through space. It is an excitation in an electron field that fills the universe. And the reason every electron in your body is precisely identical to every electron in a star 10 billion light-years away is that they are all the same kind of ripple in the same underlying thing. The same is true of quarks. The same is true of neutrinos, which are so reluctant to interact with anything that roughly 100 trillion of them pass through your body every second without touching a single atom of you. The same is true of the Higgs field, which was confirmed at CERN in 2012, when they finally produced its ripple, the Higgs boson, at a mass of around 125 giga-electronvolts. The picture that emerged, and has never since been overturned, is that the universe is made of fields. Not particles moving through empty space, but fields filling all of space, and particles are what you get when a field is disturbed. A particle is a quantum of a field. That is not a poetic description of it, that is the technical content. It is worth pausing on how counterintuitive that is at everyday scales, because the reason it took so long to notice is that the pieces are absurdly small. A single packet of green light carries about 2.5 electron volts of energy. A 100-watt bulb throws out something on the order of 100 billion of them every second. At that rate, the graininess is completely invisible, in the same way that a photograph in a newspaper looks continuous until you put a magnifying glass on it and find dots. Nature has been dotted the whole time. Our senses are simply too coarse to resolve the dots, and every instrument that ever got fine enough found them. So now put those two halves of the century side by side. On one side, Einstein has told us that gravity is the curvature of space-time, and that curvature is described by a mathematical object called the metric, a field spread through all of space, telling you the shape of things at every point. On the other side, every single other field anyone has ever examined has turned out to be quantized. You can see the argument coming, and it is very hard to escape. If the metric is a field, and every field comes in quanta, then the metric comes in quanta, and those quanta are what gravity is made of. The name arrived before the theory did. In 1934, two Soviet physicists, Dmitry Blokhintsev and F.M. Galperin, used the word graviton in print, in a paper about neutrinos, of all things, in a Soviet philosophy of science journal. The particle did not exist. There was no theory of it, no calculation supporting it, and certainly no experiment. It had a name and nothing else, which is a curious way for something to enter physics. The first person to actually try the calculation was Leon Rosenfeld, 4 years earlier, in 1930. He set out to compute the gravitational self-energy of a photon, how much a particle of light weighs, in effect, by virtue of its own gravitational field. The answer came back infinite. The very first quantum gravity calculation ever performed produced a divergence, immediately, on the first attempt. We are going to see that same divergence come back in a far more sophisticated form much later tonight, and it is worth noting now that the problem announced itself on day one and has never fully gone away. And then there is Matvei Bronstein, who is one of the people this story quietly belongs to. In 1935 and 1936, Bronstein worked out that gravity could not simply be quantized by copying what had worked for electromagnetism. His argument turned on the fact that in electromagnetism you can, in principle, make a test charge as small and light as you like in order to measure the field without disturbing it. In gravity you cannot, because the measuring device has mass, and mass is the source of the field. Push the precision far enough, and the apparatus collapses into a black hole. He saw, in 1935 that there is a fundamental limit to how sharply the gravitational field can be defined at all, an idea that would not become mainstream for decades. Bronstein was arrested in the summer of 1937 during the Great Purge and executed in February of 1938. He was 31 years old. The work sat largely unread for a generation. The subject really began in earnest in January of 1957 at a conference in Chapel Hill, North Carolina, formerly titled The Conference on the Role of Gravitation in Physics, the first meeting ever convened specifically on this problem. Richard Feynman stood up there and made an argument that has haunted the field ever since. Suppose, he said, that gravity is not quantized. Suppose it is a classical field responding to matter. Then take a particle and put it into a superposition. Send it through two slits at once, the way quantum mechanics permits. What does its gravitational field do? If the field is classical, it must point somewhere definite. And if it points somewhere definite, you could, with a sensitive enough instrument, look at the field and find out which slit the particle went through. And if you can find that out, the interference pattern must vanish. Quantum mechanics would break. So either gravity is quantum, Feynman argued, or quantum mechanics is wrong. Almost everyone in the field has taken the first branch ever since. Which brings us to the obvious problem. We have a name, we have an argument for why the thing must exist, and we have not the faintest hope of producing one. So how does anyone know what it is like? The answer to that turns out to be one of the most remarkable pieces of reasoning in 20th century physics, and it does not require a single experiment. Part 4. How to describe a particle nobody has seen. I want to put you somewhere for a moment, and I want you to stay there for the length of this next passage. You are in a room in the middle of the 1930s. There is a blackboard. There is no detector, because no detector could help you. There is no data, because there is no data to have. In front of you is a list, and on the list is everything that gravity is observed to do. Nothing else. That is your entire supply of information, and you are going to build a particle out of it. The first item on the list says that gravity reaches across the solar system. It reaches across the galaxy. Its strength falls off as the square of the distance, and it keeps doing that for as far as anyone has ever been able to check. You write down the consequence. A force carrier with mass produces a range limit. The strength does not simply thin out with distance. It dies exponentially past a certain point, and that point is set by the carrier's mass. The heavier the carrier, the shorter the leash. This is why the weak nuclear force does not reach past the width of a nucleus. Its carriers are enormously heavy. Gravity has no leash, therefore your particle has no mass. You write down 0 and you underline it. The second item says what gravity responds to, not charge, because neutral things fall, not color, because electrons fall. It responds to mass and energy. And in Einstein's theory, the source is a specific mathematical object called the stress-energy tensor, which needs two indices to write down. It carries information about energy, momentum, pressure, and stress, all at once. And to keep track of that, you need a two-slotted object rather than a one-slotted one. The electromagnetic field couples to a one-slotted source, the electric current, and the photon carries 1 unit of spin. Yours couples to a two-slotted source. You write down spin 2. The third item says that gravity pulls. It has never been observed to push. Not once, not for any pair of ordinary objects, anywhere. You go and check what spin does to the sign of a force. It turns out, and this is a genuine result from the mathematics of particle exchange, not a rule of thumb, that when the exchanged particle has odd spin, like a photon, two things carrying the same sign of charge repel each other. That is why two electrons push apart. When the exchanged particle has even spin, Two things carrying the same sign of source attract. And since there is no such thing as negative mass or negative energy in ordinary matter, everything is the same sign, and everything attracts everything. You look at your blackboard. You wrote down 2. 2 is even. Gravity pulls because 2 is an even number. The fourth item is the strange one. Gravity does not care what things are made of. A feather and a hammer, dropped together on the moon by David Scott in 1971 in front of a television camera, land together. Different materials, different internal structures, different binding energies, and they fall identically to within a few parts in 10 to the 13 when you measure it properly in a laboratory. Whatever your particle is, it must couple to absolutely everything with exactly the same strength. And here is where it stops being a list and becomes something remarkable. Because you might think that universal coupling is a fourth independent thing you have to put in by hand. It is not. In 1964, Steven Weinberg proved that it comes free, using nothing but Lorentz invariance, the requirement that physics look the same to observers moving at different constant speeds, and the mathematical structure of how scattering probabilities behave when the emitted particle has vanishingly small energy. He showed that a theory containing a massless spin 2 particle is only consistent if that particle couples to everything with the same strength. If it did not, the mathematics would produce nonsense. Sit with that for a second, because it is a genuine reversal. The equivalence principle, the observed fact that all objects fall at the same rate, the fact that Galileo is supposed to have tested from a tower in Pisa, the fact that Einstein built general relativity on top of, the fact that a feather and a hammer land together in the lunar dust, is not an assumption in this picture. It is a consequence. It falls out of the requirement that a massless spin 2 particle be able to exist at all in a universe with special relativity in it. You did not put it in, you got it out. And Weinberg's argument does more than that. It also rules out the alternatives. He showed that massless particles of spin 3 or higher cannot couple to ordinary matter in any consistent way at all. The mathematics forces their coupling to 0. Spin 2 is not one option among many. It is the ceiling. There is exactly one kind of massless particle that can produce a long-range universal attraction, and you have just built it on a blackboard without ever going near a laboratory. You would also, at this point, be able to say what its polarizations look like. A massless spin 2 field has 2 independent physical polarization states. They are usually called plus and cross, and they describe 2 different ways that a passing disturbance stretches space. In one, space is stretched along one axis while being squeezed along the perpendicular axis, then the 2 swap back and forth. In the other, the same thing happens, but rotated by 45 degrees. A ring of free-floating marbles with a gravitational wave passing through it would pulse from a circle into a horizontal ellipse, back through a circle into a vertical ellipse, and around again. And the spin 2 assignment does something else that is quietly checkable. It tells you what gravity is not allowed to radiate. An accelerating electric charge radiates light in what is called a dipole pattern, the simplest possible way for a field to shake off energy, one lobe out one side and one out the other. Gravity cannot do that. The reason is conservation laws. The gravitational equivalent of the dipole is the total momentum of the system, and total momentum is conserved, so it cannot oscillate, so it cannot radiate. The simplest radiation gravity is permitted is one step up in complexity, the quadrupole, a 4-lobed pattern that requires the shape of the source to change rather than just its position. And that is exactly what spin 2 demands, because a spin 2 field couples to a 2-indexed object. You can hear this in the data. When 2 black holes spiral into each other, the gravitational wave that comes out has a frequency exactly twice the orbital frequency, not equal to it. A binary going around once per second emits at 2 cycles per second. That factor of 2 is the quadrupole showing itself. As far as the wave is concerned, a dumbbell turned half a revolution looks identical to a dumbbell that has not turned at all, so one orbit produces 2 full cycles of signal. When you look at the recorded chirp of GW15914 and read off that doubling, you are reading off the spin of the graviton from a black hole collision 1.3 billion light-years away. That is not a prediction waiting to be tested. That is what LIGO measures. Those 2 polarizations are precisely the signal the detectors are built to pick apart. And they are there, exactly as a massless spin-2 field says they must be. So step back and look at what is on the blackboard. And that 0 on the mass line is not merely assumed anymore. It is measured, or rather bounded, and bounded hard. If the graviton had even a whisper of mass, gravitational waves would disperse. The high-frequency parts of a signal would travel at a slightly different speed from the low-frequency parts, and a chirp that left a black hole merger as one clean sweep would arrive smeared. Across all 3 completed observing runs, the LIGO, Virgo and Cagra collaborations have looked for that smearing in roughly 90 merger signals and not found it, which puts the graviton mass below about 1.27 times 10 to the minus 23 electron volts. That is around 100 billion times lighter than an electron. 0 remains the best available reading. Mass, 0. Spin, 2. Polarization states, 2. Coupling, universal, derived rather than assumed. Sign of the force, always attractive, because the spin is even. Range, infinite. Speed of propagation, the speed of light, because that is what massless things do. Every one of those was obtained by reasoning from what gravity is observed to do, plus the requirement that quantum mechanics and special relativity both hold. Not one of them came from detecting a graviton, because nobody ever has. This is worth being precise about, because it is easy to hear all of that and conclude that the graviton is a guess with good manners. It is not a guess. It is closer to being a theorem. If gravity is a field, and if that field is quantum, and if special relativity holds, then the quantum of that field has these properties and no others are available. The room for disagreement is not in the properties. The room for disagreement, as we will get to, is entirely in that middle if, whether the gravitational field is quantum at all, and in the deeper question of whether the graviton is a fundamental object or something that only looks like one from a distance. But if you had asked, in 1935, for a physicist to describe an object that no experiment would ever produce, they could have handed you a complete specification sheet. And 90 years later, with detectors that can measure a length change 1,000th the width of a proton, not a single line on that sheet has needed correcting. There is only one number left to add, and it is the number that ruins everything. Part 5. 1 followed by 36 zeros. Take 2 protons and hold them a millimeter apart. They are both positively charged, so they push each other away electrically. They both have mass, so they pull each other in gravitationally. Both forces are acting, at the same instant, between the same 2 objects, across the same distance. Both fall off as the square of the separation, so the ratio between them does not change no matter how far apart you move them. Compare the 2 numbers. The electrical repulsion is larger than the gravitational attraction by a factor of about 10 to the 36. I want to be careful here, because a number like that goes past the point where the human mind registers it as a quantity at all. It becomes a shape on a page. So let me convert it into something you can actually stand next to. 10 to the 36 is a 1, followed by 36 zeros. If you counted at 1 number per second, without sleeping, without stopping, you would not reach it in the age of the universe. You would not reach it in a billion ages of the universe. You would need to run the entire history of the cosmos, from the Big Bang to now, roughly 100 billion times over. Or try it as distances. The diameter of a proton is about a millionth of a billionth of a meter. The diameter of the observable universe is about 880,000 billion meters. The ratio between the smallest thing physics routinely talks about and the largest thing physics can see is around 10 to the 41. So the gap between electromagnetism and gravity, acting on the same two particles, is within a few factors of the gap between a proton and the entire visible universe. That is the number. That is what makes gravity what it is. And there are two consequences, and they run in opposite directions, which is the part that always surprises people. The first consequence is the obvious one. Gravity is stupendously, almost embarrassingly weak. You can demonstrate this in your kitchen. A fridge magnet weighing a few grams will hold itself to a steel door, and in doing so, it is beating the gravitational attraction of the entire planet Earth, 6 times 10 to the 24 kilograms of rock and iron, pulling on that magnet with everything it has, and losing to a scrap of ferrite the size of a coin. Bend down and pick up a paperclip with that magnet, and you have just watched a few grams of material outmuscle the whole planet. Every time you stand up out of a chair, the electromagnetic forces in your leg muscles overpower the gravitational pull of a world. The second consequence is the one that makes the universe look the way it does. Gravity runs everything at large scales. It assembles stars, sets their lifetimes, collapses their cores, builds galaxies, arranges galaxies into clusters, and clusters into filaments hundreds of millions of light years long. The weakest force by a factor beyond comprehension is also the force that decides the architecture of everything. Both of those are true at once, and the reason is a single structural fact. Gravity has no negative charge. Electric charge comes in two kinds, and matter in bulk is almost perfectly balanced between them. Every atom in your body carries a nucleus of positive charge and a cloud of electrons of negative charge, and from any distance at all, the two cancel to an extraordinary degree. If you removed just 1% of the electrons from your body and 1% from a person standing an arm's length away, the repulsion between you would be enough to lift a weight comparable to the Earth's mass. That is how ferociously electromagnetism cancels itself. It is so strong that reality has arranged for it to almost entirely switch off at any scale larger than a molecule. Gravity cannot cancel. There is no negative mass, no negative energy in ordinary matter, nothing that subtracts. Every kilogram you add makes the pull larger, and it never comes back down. So the weakest force accumulates without limit, while the strong ones neutralize themselves. And by the time you get to the mass of a planet, the ranking has completely inverted. You can see how badly this weakness hurts in the laboratory record. Newton published his law of gravitation in 1687, and it took over 100 years before anyone could measure the constant sitting in front of it. Henry Cavendish finally did it in 1798, with lead spheres hung from a wire in a sealed shed, watching a beam twist by a fraction of a degree while he observed it through a telescope from outside so that his own body heat would not stir the air and ruin the result. That was the only way to see gravity acting between two objects small enough to fit in a room. And it is still the hardest constant in physics to pin down. Every other fundamental constant has been squeezed to extraordinary precision. The electron's magnetic moment is known to something like 1 part in 100,000 billion. Newton's gravitational constant is known to roughly 1 part in 50,000, and different high-quality experiments have produced values that disagree with each other by more than their stated error bars. 3 centuries after Newton, we still cannot agree on the strength of gravity to 5 decimal places, and the reason is simply that there is so little of it to measure. Now bring that back to the graviton, because this number is not just a curiosity about scales. It is the reason the rest of tonight is difficult. The strength of a force in quantum field theory is also, directly, the probability that its carrier particle will be emitted or absorbed. A strong coupling means the exchange happens readily and often. A weak coupling means it almost never happens. Photons are exchanged so freely that a warm object is pouring them out by the billion every second, and your eye can register a handful of them. Gravitons are exchanged with a probability suppressed by that same factor of 10 to the 36. Which means that gravitational effects you experience constantly, the weight of your own body, the tides, the moon in its orbit, are the summed result of a truly enormous number of unimaginably feeble individual exchanges, and no single one of them is anywhere close to noticeable. Gravity is loud only because it is made of a very large number of extremely quiet things. Remember that number, 10 to the 36. We are going to meet it twice more tonight, and it is going to mean something different each time. In a few parts, it will come back as the reason no detector can ever be built. Later, it will come back again as the reason the one experiment that could settle this whole question needs equipment nobody has yet managed to make. But before any of that, there is a piece of good news that almost nobody has been told, and it is genuinely good news, because the standard line, that physics has no quantum theory of gravity, turns out not to be true. Part 6. The quantum theory of gravity we already have. There is a sentence that gets repeated so often it has become furniture. Physics has no quantum theory of gravity. You have heard it in documentaries, read it in articles, seen it written as the opening line of 1,000 explanations. It is one of those statements that everybody knows. It is also, as usually stated, false. Not misleading, not oversimplified. False. There is a quantum theory of gravity. It was completed in 1994. It is written in gravitons. It produces specific numerical predictions with no free parameters, and it has sat in the literature for over 30 years, while the sentence above went on being repeated. Understanding what it does and where it stops is the single most useful thing you can carry out of tonight. To see how it works, you have to understand a way of thinking called effective field theory, and the easiest route in is to notice something about how you already do physics without knowing it. If you want to predict the path of a thrown ball, you do not need to know what the ball is made of at the atomic level. You do not need the standard model. You do not need quark masses. You do not need to know that the leather contains carbon and nitrogen. You need the mass, the velocity, and the air resistance. The deeper structure is genuinely there, and it genuinely does not matter, and this is not laziness. It is a mathematical fact about how physics organizes itself by scale. Short distance details average out. They leave behind small corrections that you can catalogue and, if you care, calculate. That is the whole idea. An effective field theory is a theory that is honestly and explicitly only valid below some energy, that admits it does not know what happens above that energy, and that makes exact predictions anyway, in the form of a series expansion. It is not a compromise. It is how almost all of working physics is actually done. The theory of pions and nucleons at low energy, chiral perturbation theory, is an effective field theory sitting underneath quantum chromodynamics, and it makes precise predictions without ever solving the underlying theory. John Donohue's move, in 2 papers published in 1994, one in Physical Review Letters and one in Physical Review D, was to point out that general relativity is exactly this kind of theory, and that everybody had been treating its failures as though they meant something they do not mean. Here is what he did. Take Einstein's theory. Split the geometry of spacetime into a smooth background plus a small ripple. Quantize the ripple. Treat it as a field with quanta, which is to say, gravitons. Then compute the force between 2 masses, not just from a single graviton passing between them, but including the quantum corrections. gravitons that split into pairs and rejoin, gravitons that briefly become a loop of virtual particles before continuing, all the flickering intermediate processes that quantum field theory demands you include. Ordinarily, this is where gravity is said to fall apart, and at high energies it does. But at low energies, the calculation is completely well behaved, because the corrections organize themselves neatly by size, and the leading quantum correction is not merely finite, it is unambiguous. It cannot be adjusted, tuned, or absorbed into some unknown parameter. It is a clean prediction. The result is Newton's law, with two corrections attached. The familiar gravitational potential energy between two masses, the one you learned at school, gets multiplied by a bracket. Inside that bracket is 1, plus a term that is the classical general relativistic correction, roughly 3 times Newton's constant times the total mass, divided by the separation and by the speed of light squared, and then, after that, a genuinely quantum term. That last term is the Planck length squared divided by the separation squared, multiplied by a pure number. Before we get to that pure number, notice what the middle term is, because it is quietly reassuring. That first correction, the classical one, is not hypothetical. It is the term that makes the orbit of Mercury fail to close. Mercury's closest approach to the Sun drifts forward by about 43 seconds of arc every century beyond what Newton allows, a discrepancy that was noticed by Urbain Le Verrier in 1859 and went unexplained for 56 years until Einstein's field equations produced it exactly. It is the term that bends starlight around the Sun by 1.75 seconds of arc. It is the term inside your satellite navigation. So the first line of the bracket is measured, repeatedly, to high precision, and it is correct. Which means the structure Donahue wrote down is not a speculative object. It is a series whose first term is Newton, whose second term has been confirmed by more than a century of observation, and whose third term is quantum. 2 out of 3 are in the textbooks and in your phone. The third is the one nobody has heard of. The pure number is 41 over 10 pi. I want to dwell on that fraction. Because of everything in this video, it is the thing most worth understanding and the thing least likely to have reached you. 41 over 10 pi is about 1.3. It came out of a calculation involving loops of gravitons. It contains no adjustable parameters, no fitting, no experimental input. It is a prediction of quantum gravity in precisely the sense that the anomalous magnetic moment of the electron is a prediction of quantum electrodynamics, a number that the theory hands you, whether you like it or not. And the field argued about it. Getting a coefficient like that right is delicate, and between 1994 and 2003, the exact value was revised in the literature, with the modern figure settled by Bjerrum-Bohr, Donahue, and Holstein. But nobody argues about whether the correction exists or whether it is finite. It exists. It is finite. It is calculable. Quantum gravity, in the low-energy regime, is a solved and functioning subject. So why has nobody heard of it? Because of what happens when you put numbers into it. The Planck length is 1.616 times 10 to the minus 35 meters. Squared, that is about 2.6 times 10 to the minus 70 square meters. Now divide by the separation squared. If your two masses are a meter apart, the quantum correction to the gravitational force between them is of order 10 to the minus 70. 10 to the minus 70. A decimal point followed by 69 zeros and then a digit. To put that in some kind of perspective, the most precisely verified prediction in the history of science is the electron's magnetic moment, confirmed to around 1 part in 10 to the 13. The quantum correction to gravity between two objects on a table is 57 orders of magnitude below that. If you could improve every measurement humanity has ever made by a factor of 1 trillion, and then do it again, and then do it again, and keep going, you would still be nowhere near. And it is not for want of trying to find somewhere the effect might be bigger. The correction grows as the separation shrinks, since it depends on the Planck length divided by the distance, squared. So people have asked whether it might matter close to a black hole, or in the interior of a neutron star, or in the first fractions of a second of the universe. The answer in every ordinary astrophysical case is no, by an enormous margin. Even at the horizon of a stellar mass black hole, the ratio of the Planck length to the horizon radius is around 10 to the minus 39, and squaring that leaves you worse off than before. There is exactly one place in the universe where the correction becomes the whole story, and it is a region a Planck length across, at the center of a black hole, or at the beginning of time, which is to say, precisely the two places nobody can look. And that is the shape of the situation, and it is a genuinely strange shape. We do not have a quantum theory of gravity that fails. We have one that works, that is exact where you are sitting, that produces a real number, and that describes an effect so small the universe has effectively arranged for it to be inaudible. The theory is not missing, the theory is silent. Sit with that for a moment, because there is something almost vertiginous in it. For 100 years the story has been told as an absence, as a hole in physics, a missing piece, the great unfinished business. And the truth is closer to this. The piece is there. It fits. It has been there since 1994, and it makes a prediction that no instrument that could ever exist will be able to hear. The gap between having the answer and being able to check it is 70 orders of magnitude wide. What we lack is not a quantum theory of gravity. What we lack is a quantum theory of gravity that survives all the way up. Because the moment you push the energy higher toward black hole interiors, toward the first instant of the universe, toward the scale where space-time itself is in question, the whole thing stops working. Not gradually, completely. And the reason it stops working is the most interesting property gravitons have, and it is the one property that no other force carrier shares. Part 7. Where we stand halfway down. Let us stop for a moment and put the pieces on the table together, because we are about halfway through, and the second half goes somewhere quite different from the first. We started with a question that sounded simple. What is gravity made of? And we have collected 3 answers, and none of them cancels the others out. They stack. The first answer was Einstein's, and it was to deny the question. Gravity is not a force. Nothing passes between the earth and your body. There is a shape to space and time, and things follow the straightest available line through that shape. And what you call falling is what going straight looks like when the geometry is curved. On this account, asking what gravity is made of is a category error, like asking what the equator is made of. And the evidence for this picture is overwhelming. It predicted the bending of starlight, the drift in Mercury's orbit, the exact waveform of 2 black holes colliding 1 billion light-years away, and the timing correction your phone applies to satellite signals every second of every day. It is not a theory anyone is trying to escape. It is the most accurate description of gravity we have. What that answer does not do is tell you what the shape is made of. It describes the behavior of the metric field beautifully and says nothing about its substance. It is an answer that differs. The second answer came from the rest of 20th century physics, and it is much harder to argue with than it first appears. Every field anyone has ever examined closely turned out to be granular. Light comes in photons. The electron field comes in electrons. If the geometry of space-time is a physical field, and general relativity insists that it carries energy, that it ripples, that those ripples travel at a finite speed and arrive at our detectors, then it should come in quanta too. Those quanta are gravitons, and we can specify them completely. Massless, spin 2, 2 polarizations, universally coupled, always attractive. Every one of those properties was derived from constraints rather than measured, and every one of them has survived a century of observation without correction. And Feynman's argument at Chapel Hill in 1957 still stands. If gravity were not quantum, you could use its field to find out which slit a particle went through, and quantum mechanics itself would come apart. The third answer is the one nobody talks about, and it is that we can actually calculate. Treat general relativity honestly as a theory valid below a certain energy. Quantize the ripples, include the loops, and you get real quantum corrections to Newton's law with a coefficient of 41/10 pi and no adjustable parameters at all. That is a working quantum theory of gravity. It has been working since 1994. Its predictions are around 10 to the minus 70 at everyday distances, which is why you have never heard of it. And laid out side by side, the three answers are not really rivals. They are the same answer, viewed from three distances. Einstein describes the shape. The graviton picture describes what the shape is made of when you look closely. The effective field theory tells you how much the graininess actually matters at the scale you live on, and the answer is not at all, by 70 orders of magnitude. A geologist, a chemist, and a particle physicist looking at the same rock would give you three different accounts of it, and none of them would be wrong. There is also one number running underneath all three, and we met it 2 parts ago. 10 to the 36, the ratio between the electrical and gravitational forces on 2 protons. That number is why the effective theory's predictions are inaudible. It is about to become the reason no detector can be built, and much later tonight it will turn up a third time, as the reason the one experiment that could settle everything needs equipment nobody has managed to build yet. The same quantity keeps reappearing wearing different clothes, and each time it costs us something else. So the honest state of play at the halfway mark is not ignorance, it is something stranger. We have a name for the constituent, a complete specification for it, and a functioning theory that uses it. And the theory's predictions are inaudible, and the theory itself expires at high energy. That word expires is where the second half begins. Because everything I have described so far is a theory of small ripples on a smooth background. Weak gravity, the gravity of a table, a planet, a pair of orbiting black holes seen from a long way off. Push into the regions where gravity is genuinely strong, the last Planck length before a singularity, the first Planck time of the universe, and the picture does not degrade gracefully. It collapses. And it collapses for a reason that comes directly from the graviton's own nature, from a property that sets it apart from every other force carrier in the inventory. The photon is innocent of the field it carries. The graviton is not. Part 8. The point where the answer expires. A photon is electrically neutral. That sentence sounds like a small technical detail, and it is one of the most consequential facts in physics. The photon carries the electromagnetic force, and it does not itself carry electric charge. It is a messenger that is not a member of the club it delivers messages to, which means photons do not interact with each other. 2 beams of light cross in a dark room and pass straight through, undisturbed, each one behaving as though the other were not there. You have seen this your whole life, and never thought about it. Torch beams cross. Sunlight and lamplight occupy the same air. Nothing collides. That neutrality is the reason quantum electrodynamics is such a well-mannered theory. When you calculate in it, the corrections get smaller in an orderly way, each one suppressed by a factor of roughly 1/137 relative to the last, and you can chase the series as far as your patience allows. It is why the electron's magnetic moment has been calculated and confirmed to around 1 part in 10 to the 13, the most precisely verified agreement between theory and experiment that human beings have ever achieved. Now ask what a graviton carries. Gravity couples to energy. All energy, not mass, not charge, not color. Energy, in every form it takes. And a graviton has energy, because everything that moves and carries momentum does. So a graviton is a source of gravity. Read that again slowly, because it is the whole problem. The carrier of the gravitational force is itself gravitating. The messenger is a member of the club. Gravitons attract gravitons. Every graviton passing between two masses is itself emitting and absorbing further gravitons. And each of those does the same, all the way down. Nothing else in the standard inventory behaves like this in quite so severe a way. The gluon does something similar. Gluons carry color charge and interact with each other, which is why the strong force behaves so strangely, and why you can never pull a single quark out of a proton. That self-interaction was hard enough that it took most of the 1970s and a Nobel Prize to sort out. Gravity's version is worse. And it is worse for a reason that has nothing to do with how hard the sums are. The reason is that Newton's constant has the wrong units. In particle physics, coupling constants that produce well-behaved quantum theories are pure numbers, dimensionless, with no units attached. The fine structure constant that governs electromagnetism is about 1/137, and it is just a number. It is the same number regardless of what energy you are working at, up to a slow drift. Newton's constant is not a pure number. In the natural units physicists use, it carries dimensions of length squared, or equivalently 1/energy squared. And that has a devastating consequence, because it means the strength of a gravitational quantum process depends on the energy you are working at. Every time you go to a higher order in the calculation, you pick up another factor of Newton's constant, and to make the units come out right, that factor has to be multiplied by the energy squared. At everyday energies that suppression is total, this is exactly why the correction Donahue calculated is 10 to the minus 70. But run the energy up, and the suppression turns into an amplification. Each successive correction becomes larger rather than smaller. The series that was so beautifully convergent at the scale of a table becomes divergent at the scale where quantum gravity actually matters, and the specific energy where the crossover happens is the Planck energy, 1.22 times 10 to the 19 giga-electron-volts. Physicists found this out in the most concrete way possible, by doing the calculation and watching it fail. In 1974, Gerard Hooft and Martinus Veltman, who would share a Nobel Prize 25 years later for related work, carried out the one-loop calculation for pure gravity, gravity with no matter present at all. And they found something encouraging. The infinities that appeared could be absorbed. They could be swept away by redefining the fields, which meant that at that level, gravity was finite. For a brief period, this looked like it might be the beginning of good news. The good news lasted as long as it took to add anything else to the universe. Put in a single scalar field, put in electromagnetism, put in any matter at all. The one-loop finiteness breaks immediately, and the divergences come back and cannot be removed. So the encouraging result applied only to a universe containing nothing but gravity, which is not the universe we are in. The decisive calculation came a decade later. Mark Goroff and Augusto Sagnotti pushed the computation to 2 loops, and this was not a calculation anybody could do with a pencil. They wrote custom computer algebra programs in C specifically for the job. It is one of the earliest large-scale uses of machine algebra in theoretical physics. And in 1985 and 1986, they published the answer. There is a divergence at 2 loops in pure gravity. It is a term built from 3 powers of the Riemann curvature tensor, and it comes with a coefficient of 209 over 2880 divided by 16 pi squared. It is not removable by any field redefinition. It is simply there. Anton van der Ven confirmed the result independently in 1992. it has stood ever since. What that means in practice is that gravity is non-renormalizable. In a renormalizable theory, all the infinities that arise can be tidied away into a small, fixed number of quantities that you measure once: the electron's mass, its charge, and thereafter, the theory predicts everything else forever. In a non-renormalizable theory, each new order of the calculation throws up new infinities, requiring new parameters, and each new parameter has to be fixed by a new experiment. 2 loops needs 1, 3 loops needs more. To make a single reliable prediction at the Planck scale, you would need to have measured an infinite number of constants first. And since each measurement would itself require Planck energy experiments, the whole enterprise eats its own tail. So the answer we built so carefully has an expiry date printed on it. Gravity is made of gravitons, up to about 10 to the 19 giga-electronvolts, and not one step further. It is worth knowing how far away that ceiling actually is, because the number is not the kind of gap that better engineering closes. The Large Hadron Collider, the largest machine ever built, a ring 27 kilometers around, buried under the border between France and Switzerland, collides protons at 13.6 tera-electronvolts. The Planck energy is about 15 orders of magnitude higher. If you tried to reach it by simply building a bigger version of the same machine, the ring would have to be somewhere in the region of a light year, across at the most optimistic estimate, and thousands of light years across, on more realistic assumptions about the magnetic fields you could sustain. This is not a funding problem. There is no version of human civilization that builds that. There is one serious escape route worth naming, because it would change the verdict entirely if it were true. In 1976, Steven Weinberg, the same person whose 1964 argument gave us the graviton's universal coupling, suggested that gravity might be what he called asymptotically safe. The idea is that the coupling strength does not actually run away to infinity at high energy, but instead approaches a fixed value, in which case the theory would be predictive all the way up, despite being non-renormalizable in the conventional sense. 50 years later, the program is still alive, still producing evidence in its favor from numerical studies, and still not settled. If Weinberg was right, the graviton picture never expires at all. There is one piece of history worth holding on to here, because it stops this being simply a defeat. In 1933, Enrico Fermi wrote down a theory of beta decay, the process by which a neutron turns into a proton. It worked. It made correct predictions for decades. It was also non-renormalizable in exactly the way gravity is, with a dimensionful coupling constant and a series that blows up at high energy. And for years that was regarded as a fundamental sickness. It was not a sickness. It was a signpost. Fermi's theory was the low-energy shadow of something perfectly healthy underneath, the electroweak theory, with the W and Z bosons as real particles, entirely renormalizable and confirmed at CERN in 1983. The breakdown of Fermi's theory was not telling physicists that the theory was wrong. It was telling them the energy scale at which something new appears. That is the most defensible reading of where gravity stands. The failure at the Planck scale is not evidence that gravitons do not exist. It is evidence that something else exists at that scale, and that gravitons are what it looks like from below. Which raises the obvious question, and it is the question that would settle everything. If we cannot reach the Planck scale, can we at least catch a single graviton? Just one. Not a beam, not a flux, not a statistical excess. One. The answer to that turns out to be the strangest result in this entire subject. Part 9. The detector that collapses into a black hole. Freeman Dyson spent a long time on a question that most physicists were content to leave alone, and he kept coming back to it in lectures and essays over several decades. The question was not whether we have built a graviton detector yet. It was sharper than that, and much less comfortable. Is the graviton, even in principle observable. Is there any apparatus that could exist in this universe, built from anything, of any size, given any amount of time, that could register a single one? The question matters more than it might appear. Physics has generally taken the view that a thing which cannot in principle be observed is a thing whose existence is a matter of convention rather than fact. Dyson's suspicion was that the graviton might sit on the wrong side of that line, that it might be, in his framing, a mathematical convenience rather than a physical object, because nothing in this universe could ever interact with one strongly enough to notice. In 2006, Tony Rothman of Princeton and Stephen Bown of Haverford College published a paper in Foundations of Physics, taking the question seriously and working through the numbers. What they found is one of the strangest results anywhere in modern physics. I want you to come with me and stand inside their calculation, because it is a place worth visiting. You are in orbit around a neutron star. Below you, a sphere of matter about 20 kilometers across, containing more mass than the Sun, spinning, its surface gravity 200 billion times what you feel standing on a pavement. Space here is genuinely warped. Gravitational radiation is pouring out of this system and passing through you continuously. And you have brought a detector, not a realistic one, an idealized one, the best that physics permits, running on the gravitational equivalent of the photoelectric effect. It has the mass of Jupiter, 318 Earths of material, assembled into a single instrument, operating at 100% efficiency, which is to say that every graviton that could possibly be absorbed is absorbed. Nothing is wasted. You switch it on, and you wait. Nothing registers. A year passes. Nothing. 1,000 years. The neutron star cools slightly and goes on spinning. 1,000,000 years. The instrument sits in its orbit, absorbing nothing worth recording. 1,000,000,000 years. The galaxy turns a handful of times. Stars form in the arms below you and burn out. 10 billion years. The universe is now twice its present age, and your Jupiter mass detector, at perfect efficiency, in one of the most violent gravitational environments that exists, has still not reliably logged a single graviton. That is the first result. To detect one graviton would take longer than the universe has existed. But the second result is the one that closes the door properly, and it has nothing to do with rates at all. Any detector has to sit somewhere, and everywhere is flooded with neutrinos. Roughly 100 trillion of them pass through your body every second, and neutrinos are already famous for barely interacting with anything. The trouble is that barely is enormously more than gravitons manage. Any signal your detector produced would be buried under neutrino events by a margin so large that the graviton count would be invisible in the noise. So you shield it. That is what physicists always do. Put the experiment underground, wrap it in lead, get the background down. And here the calculation delivers its verdict. To block enough neutrinos, your shield has to be thicker than the distance a neutrino typically travels through matter before interacting. For ordinary materials, that distance is measured in light years. So you would need a shield made of ordinary density matter, surrounding your detector, several light years thick. Assemble that much matter in one place, and it does not shield anything. It collapses, under its own gravity, into a black hole, long before it ever protects an instrument from anything. That is the shape of the wall, not a limit of funding, or of engineering, or of the current state of technology. The universe is arranged such that the apparatus required to see the constituent of gravity destroys itself by the very property it is trying to measure. Gravity is too weak to detect, and matter is too gravitational to shield with, and those two facts are the same fact. Rothman and Bown are careful in the paper. They allow that a sufficiently idealized thought experiment can be constructed in which one graviton is detected. You can always cheat in a thought experiment. Their point is that as soon as anything resembling realistic physics is put in, the possibility evaporates. Dyson's conjecture, they conclude, is very likely correct. Rothman has since put it more bluntly in interviews, saying he would bet his house that nobody in this universe will ever detect a graviton. And there is an obvious objection at this point, which is worth answering directly, because it trips up almost everyone the first time. If gravitons are undetectable, how did LIGO detect gravitational waves? The answer is the difference between hearing an orchestra and catching one molecule of air. A gravitational wave is not one graviton. It is a coherent flood of them, all in step, all with the same phase, behaving collectively as a smooth classical wave, in exactly the way that a radio broadcast is a flood of photons, so numerous and so well aligned that nobody thinks of it as a stream of particles at all. When the two black holes that produced GW 11514 merged, they radiated about 3 solar masses of energy as gravitational waves. Each individual graviton in that signal, at a frequency of 100 or so cycles per second, carries an energy of order 10 to the minus 31 electron volts. Divide one into the other, and you are dealing with something in the region of 10 to the 78 individual quanta arriving. That is why the wave was detectable, and the graviton is not. We have measured gravitational radiation superbly. We have measured its speed to 1 part in 1,000 trillion. We have watched black holes collide, and we have never come within 100 orders of magnitude of resolving the grain in the picture. Seeing the wave and seeing the quantum are not the same achievement, and only one of them has happened. Now let this settle for a moment, because it deserves a moment. Every fundamental constituent of matter humanity has ever proposed has eventually been produced, counted, or cornered. The electron was fired down a tube by J.J. Thomson in 1897. The neutron came in 1932. The neutrino was postulated in 1930 by Wolfgang Pauli, who apologized in writing for inventing a particle he thought could never be detected, and it was detected 26 years later by Cowan and Reines beside a nuclear reactor. The Higgs boson was predicted in 1964 and produced in 2012, 48 years later, at a cost of billions, and a machine 27 kilometers around. The quark comes closest to being an exception, since a free quark can never be isolated, but quarks announce themselves constantly, in deep inelastic scattering, in jets, in the entire structure of hadron physics. We have never seen one alone, and we know they are there beyond any doubt. The graviton may be the first thing in the history of the subject for which none of that is available. Not yet undiscovered, not merely difficult. Structurally out of reach, by an argument about neutrino shielding and gravitational collapse that a physicist can sketch on the back of an envelope. There is a difference between not yet and not ever, and it is worth feeling that difference rather than simply noting it. Not yet is the ordinary condition of science, and it is a hopeful one. Pauli's apology turned out to be premature by 26 years. Higgs waited half a century and was vindicated. Almost everything in physics that was once called undetectable has since been detected by somebody with better instruments and more patience. This one appears to be different, and what makes it strange rather than simply sad is that we are not in the dark about the thing. We can tell you its mass to 23 decimal places of an electron volt. We can tell you its spin, its polarizations, its coupling, the sign of the force it produces, and why that sign is what it is. We can calculate with it and get the right answer. We know almost everything a physicist could want to know about an object we may never be allowed to hold, except that in 2024, somebody found a crack in the wall. Part 10. The Crystal That Jumps One Step. In August of 2024, a paper appeared in Nature Communications with 4 authors, Germain Tobar, Srinath Manikandan, Thomas Beitel, and Igor Pikovsky, and it did something that had not been done in nearly 20 years. It reopened a question the field had quietly filed as closed. Their argument does not overturn Rothman and Baun. They are careful about this, and it matters. What they do instead is notice that everyone had been asking a slightly harder question than they needed to. Rothman and Baun asked whether you could capture a graviton out of the general gravitational radiation background, a lone particle arriving from nowhere in particular, absorbed by a detector, the way a photodetector catches a stray photon. That, they showed, is hopeless. Tobar and his colleagues asked a different question. Suppose you do not try to catch a graviton from the background. Suppose instead you sit underneath a real, loud, known gravitational wave from a real astrophysical event, two black holes merging, the kind of signal LIGO already records several times a month, and ask whether the energy that wave delivers to a piece of matter arrives smoothly or in steps. That reframing changes everything, and it changes it in a way that has a direct historical precedent. Think about how we learned that light was quantized. Nobody caught a photon out of empty space and put it in a jar. What happened is that Einstein looked at what light does when it lands on a metal surface and noticed that the energy is not delivered continuously. It comes in packets, and the effect switches on abruptly at a threshold color rather than growing smoothly with brightness. The quantization was inferred from the granularity of the exchange, not from isolating a particle. Tobar's proposal is the gravitational version of exactly that, and the authors say so plainly. The observation of single graviton absorption would be the gravitophononic analog of the photoelectric effect. Here is the instrument. Picture a heavy cylinder of crystal, suspended in vacuum, cooled to within a hair of absolute zero, cooled so thoroughly that its vibrations have settled into their lowest possible quantum state, the ground state, in which the bar is as still as the laws of physics will permit anything to be. This is not ordinary stillness. Ordinary matter at room temperature is a riot of thermal motion. This bar has had essentially all of that removed. Its vibrational energy can now only take specific discrete values, like the rungs of a ladder, and it is sitting on the bottom rung. It has a lineage, this object. In the 1960s, Joseph Weber built aluminium bar detectors of roughly this shape and announced that he had detected gravitational waves with them. Nobody could reproduce his results, and the episode became one of the standard cautionary tales in experimental physics. But the concept was never wrong, only premature. Weber's bar has come back, 60 years later, cooled into the quantum regime and read out by instruments he could not have imagined. Now the wave arrives. Two black holes, somewhere out in the sky, have finished a spiral that lasted millions of years, and the ripple from the last fraction of a second of it has been traveling toward us since before there were people. The bar does not begin to hum smoothly. It jumps. One rung, a single discrete step up the ladder of allowed energies. And the third piece of the proposal is the part that makes this different from anything Weber could have done. Rather than measuring the bar's amplitude, you monitor it continuously with quantum sensing, watching not for a swelling vibration, but for the instant of the transition itself, the moment of the jump, caught as it happens. That is the experiment. Stimulated absorption of a single quantum of gravitational energy, resolved as a quantum jump, in a device sitting on a bench, rather than orbiting a neutron star. The word doing the heavy lifting there is stimulated, and it is worth pulling out, because it is the entire reason this escapes the Rothman and Baun verdict. There are two ways a system can absorb a quantum: spontaneously, from a sparse background, one lonely particle wandering in. That is what the Jupiter mass detector was waiting for, and the rate is catastrophically low. Or by stimulated absorption, in the presence of an intense field, where the probability of the transition is multiplied by the number of quanta already present. This is not exotic physics. It is the same effect that makes a laser work, running in reverse. The more photons are already in the mode, the more readily another one is exchanged. Now recall the number from the last part. A gravitational wave from a black hole merger arriving at Earth contains something like 10 to the 78 gravitons. The wave is intense beyond any reasonable use of the word, even though its effect on the detector is a length change smaller than a proton. So the stimulated absorption rate is enhanced by a factor comparable to that occupation number, and the impossible becomes merely extremely difficult. The other lever is mass. The coupling of a resonator to a passing gravitational wave grows with the mass of the bar and with its length, which is why the proposal calls for a heavy object rather than a delicate one. The opposite instinct from most quantum experiments, where you keep things small to keep them coherent. Here you want something substantial, and cold, and quiet, all at once, which is precisely the combination that makes it hard. And now the part where the channel has to be honest with you, because this is a place where popular coverage went further than the physics does. Observing that jump would demonstrate that energy is exchanged between the gravitational field and matter in discrete units. That is a real and significant result, and nobody should undersell it. But it is not the same as isolating a graviton, and there is an argument, pursued seriously in the literature since, including work in Physical Review D, examining exactly this inferential step, about whether it would strictly prove that the gravitational field itself is quantized, or only that the detector is quantized and is responding to a classical wave in discrete gulps, because detectors do that. That distinction sounds like hair-splitting. It is not. It is the same objection that was raised about the photoelectric effect, and the honest history is that the photoelectric effect alone did not settle the quantum nature of light either. It took Compton's scattering and then anti-bunching experiments decades later to close that argument fully. The gravitational version would very likely follow the same road. A first suggestive result, then years of people trying to explain it another way, then eventually a measurement that cannot be explained another way. Also worth saying plainly, this has not been done. It is a proposal. The resonator masses, the cooling, the continuous quantum readout at the required sensitivity, each of those is at or beyond the edge of what laboratories can currently achieve, and they have to be achieved simultaneously. But something did change in 2024, and it is worth naming precisely what. For 18 years, the settled position was that the quantum nature of gravity was permanently beyond experimental reach. A wall, not a frontier. That position is no longer settled. There is now a serious, peer-reviewed proposal for how a laboratory could see the graininess of gravity, and the argument about whether it would work is a live scientific argument rather than a closed one. Which brings us to the question we have been circling since the beginning. All of this assumes the graviton is the fundamental answer. What if it is not? Because 3 of the most serious theories in physics say that when you look underneath the graviton, you do not find a graviton at all. Part 11. 4 rival answers to the same question. Everything so far has treated the graviton as the answer. Now we go one level down and ask what the graviton is made of, or whether it is made of anything, or whether it exists at the bottom at all. There are 4 serious programs. They have been running for decades. They are pursued by careful people. And the thing to notice about them, which is more interesting than any of their individual claims, is that they do not merely disagree about the answer. They disagree about what kind of thing the answer is. One says a vibration, one says a network, one says an ordering, one says a correlation. Only one of the 4 still contains a graviton in any fundamental sense. The first is string theory, and it did not set out to be a theory of gravity at all. It began in the late 1960s as an attempt to describe the strong nuclear force, before quantum chromodynamics existed. The idea was to model hadrons as vibrating strings rather than points. It had promise, and it had a persistent embarrassment. The spectrum of vibration modes kept producing a massless particle with spin 2, and nobody wanted it, because no such particle appears anywhere in nuclear physics. It was a defect. People tried to get rid of it and could not. In 1974, Joël Shirk and John Schwartz, and independently, at roughly the same time, Tamiaki Yoneya in Japan, made the suggestion that turned the defect into the point. The unwanted massless spin 2 state was not a flaw in a theory of the strong force. It was the graviton, and the theory was not a theory of nuclear physics, but a theory of everything. Nobody paid much attention for a decade. The proposal sat largely ignored until 1984, when Michael Green and Schwartz showed that certain fatal-looking mathematical inconsistencies cancelled exactly, and the field changed direction almost overnight. In this picture, the answer to our question is a different shape from anything we have considered. The graviton is not elementary. It is a note, a closed loop of string, vibrating in one particular way, and other vibrational patterns of the same string are other particles, the photon, the electron, the quark. Everything is the same object, doing different things, in the same way that a violin string produces different notes without becoming a different string. And the mode cannot be removed. This is the part that keeps physicists interested after 50 years. Every free closed string theory contains a massless spin 2 state, and so does every theory of interacting strings. No assumption about gravity is put in at the start. General coordinate invariance is not an input. You write down a theory of vibrating loops with no thought of gravity whatsoever, and gravity comes out anyway, unbidden and unremovable. There is a technical payoff to this that goes to the heart of Part 8. The reason the graviton calculation breaks at high energy is that point particles can approach each other arbitrarily closely, and the interaction becomes arbitrarily violent. A string has extent. There is no arbitrarily close. The short-distance behavior that ruins the point-particle calculation gets smeared out over the length of the string, and graviton scattering amplitudes in string theory come out finite. That is the single strongest argument anyone has for the whole program. The cost is everything else. Consistency requires 10 space-time dimensions in the superstring formulation, which means 6 of them have to be curled up small enough to have escaped notice, and the number of consistent ways to do that curling is usually estimated at around 10 to the 500. That is not a number in any ordinary sense. There are perhaps 10 to the 80 atoms in the observable universe. Which of those configurations describes our universe is not determined by the theory, and there is currently no accepted method for finding out. That is the honest situation, and it is what the theory's critics point at. So string theory's answer is, gravity is made of the same stuff as everything else, vibrating differently. It is the most economical answer available, and the least testable. The second program takes the opposite route entirely. Loop quantum gravity begins from a complaint about the graviton calculation. Every step of that calculation assumed a background, a smooth space-time on which small ripples move. But general relativity's central insight is that space-time is not a stage, it is a participant. Quantizing ripples on a fixed background, the loop program argues, quietly abandons the thing that made Einstein's theory revolutionary in the first place. So instead of quantizing ripples, they quantize the geometry itself, with no background at all. The technical door in was opened by Abhay Ashtekar in 1986, who reformulated general relativity in a new set of variables that made its equations look much more like the gauge theories that had worked so well for the other forces. What came out the other side was a picture that is genuinely difficult to hold in the mind, and worth trying. The states of the theory are called spin networks. A spin network is a graph, nodes connected by links, where each link carries a label drawn from the mathematics of rotations, and each node carries an object relating the links that meet there. Roger Penrose had introduced spin networks in the early 1970s for entirely different reasons. Carlo Rovelli and Lee Smolin found them sitting at the center of quantum geometry. Here is what the picture says. The nodes are quanta of volume. The links are quanta of area. Space is not a container that the network sits in. The network is space. There is nothing between the nodes, because between is a relationship the network itself defines. And then comes the result that gives the program its teeth. Rovelli and Smolin proved, in 1994 and 1995, that in this framework, the mathematical operators corresponding to area and to volume have discrete spectra. Area is quantized, not as a modeling assumption, but as a derived consequence, in the same way that the energy levels of a hydrogen atom are derived rather than assumed. Take that in for a moment. It means there is a smallest possible non-zero area. When one link of a spin network pierces a surface, it contributes an area proportional to the Planck length squared times the square root of j times j plus 1, where j is that link's label. The smallest allowed non-zero patch is on the order of 10 to the minus 70 square meters. You cannot have half of it. You cannot subdivide it. Area comes in units, the way charge comes in units, of the electron's charge. If that is right, then space is not infinitely divisible. There is no such thing as a region smaller than the smallest node. And the smooth continuum you learned about in school is an approximation in the same way that the smooth surface of water is an approximation to a crowd of molecules. And notice what has happened to our question. In this picture there is no graviton at the fundamental level at all. Gravity is not a particle exchanged across space. Gravity is what space does, and space is a finite, countable, combinatorial structure. Something graviton-like ought to emerge when you look at the network from far enough away, in the way that sound waves emerge from a lattice of atoms, and demonstrating rigorously that it does is one of the hardest unsolved problems the program has. That is a real weakness, and it should be stated as one. The theory does deliver one result that is easy to state and hard to ignore. In its simplest cosmological models, the Big Bang singularity is replaced by a bounce. The quantum geometry refuses to be compressed past a certain density and pushes back, so the universe does not begin at a point of infinite curvature, but at a minimum size, with something before it. Ashtekar, Pavlovsky and Singh worked this out in 2006. The third program is the most austere of the four, and its answer is barely a substance at all. Causal set theory, introduced by Bombelli, Lee, Meyer, and Sorkin in 1987, says the fundamental constituents of the world are discrete events, points, if you like, but with no properties, and the only fundamental structure is the causal order between them. Which event could have influenced which? That is the entire ontology. No lengths, no durations, no coordinates. Everything else, including the whole metric of space-time, is supposed to be recovered by counting. Volume is number of elements, and geometry is order plus number. The program's most quoted moment came before the theory was even properly developed. In 1987, Raphael Sorkin argued that if this picture is right, the cosmological constant should not be zero, but should fluctuate around a small value set by the inverse square root of the number of space-time elements in the universe. He wrote down a magnitude. 11 years later, in 1998, two teams, observing distant supernovae, discovered that the expansion of the universe is accelerating, and the value they inferred was in the region Sorkin had indicated. Whether that counts as a prediction is genuinely disputed, and the theory has struggled badly elsewhere. A randomly generated causal set overwhelmingly tends to look nothing like a smooth spacetime, and explaining why our universe looks continuous at all remains unresolved. And then there is a fourth answer, which I am going to keep deliberately brief because it is an enormous subject that deserves its own night rather than 4 minutes of this one. In the holographic program, Gravity inside a region of space turns out to be equivalent to a quantum theory without any gravity in it at all, living on the boundary of that region, and the geometry of the interior is built out of the entanglement structure of the boundary theory. Mark van Ramsdonk gave the sharpest version of the statement in 2010. Reduce the quantum entanglement between two parts of the boundary, and the space connecting the corresponding interior regions pinches, thins, and comes apart. Take the entanglement away entirely, and the two regions are no longer connected by any space at all. On that reading, gravity is made of correlations, not particles, not networks, not orderings, relationships between things. The caveat has to be stated, and then we move on. The fully worked examples live in a universe with a negative cosmological constant, a geometry called anti-de Sitter space, and our universe has a positive one. The dictionary that works so beautifully in that setting has not been made to work in ours. 4 answers: a vibration, a network, an ordering, a correlation. Now hold all 4 next to the question we started with, and notice how strange the situation actually is. When we asked what light is made of, everybody agreed on the category of the answer, a particle, and the argument was only about details. Here, 4 of the best defended frameworks in theoretical physics disagree about whether the answer to what gravity is made of is even the sort of thing that could be a particle. And not one of them has produced a single confirmed experimental prediction that separates it from the others. Not one. That is the honest state of the field, and anybody who tells you otherwise is selling something. Which makes the next question the only one that matters. Is there any experiment, any at all, that could tell us something real about the quantum nature of gravity? Not at the Planck scale, here, on a table. As it turns out, there might be, and it does not involve detecting a graviton. Part 12. 2 diamonds in the dark. Everything we have built tonight rests on one assumption that we have never once examined. We should examine it now, because it is the foundation, and because it is the only part of this entire subject that a laboratory can reach. The assumption is that gravity is quantum at all. Almost every physicist believes it. Feynman's argument at Chapel Hill in 1957 is the reason. If the gravitational field were classical, you could in principle read it to find out which path a particle in superposition took, and quantum mechanics would break. It is a good argument, it is not a proof, and it has never been checked. There is a competing possibility, and it has a name. Semi-classical gravity says that matter is quantum, but the gravitational field is not. That the field is a classical thing, which responds not to where a particle is, since a particle in superposition is not anywhere in particular, but to the average of where it might be, its expectation value. On that account there is no graviton. There never was one, and the last 11 parts have been an elaborate description of something that does not exist. The first person to go after this experimentally did it in 1981, with equipment that would not have looked out of place in the 1790s. Don Page and C.D. Gelker built a modified version of Cavendish's experiment, a torsion balance, a horizontal beam with small test masses at each end, hanging from a fine fibre, free to twist. Nearby, a pair of larger source masses whose gravitational pull would draw the beam one way or the other, depending on which side they were placed. The modification was the clever part. Rather than choosing which side to put the source masses on, they let a quantum event choose, a small radioactive source and a Geiger counter, and the outcome of a genuinely quantum, genuinely random decay determined the configuration. Now the 2 theories give different answers, and they give them cleanly. If gravity is quantum, then the whole apparatus ends up in a superposition of 2 configurations, and each time you look, you find one of them, with the beam twisted one way or the other, 50-50 over many runs. If gravity is semi-classical, if the field responds to the average of the mass distribution rather than to any particular arrangement, then the field should be produced by masses effectively sitting in both places at once, half-weighted on each side. Those two contributions pull the beam in opposite directions with equal strength. They cancel. The beam should not move at all. They ran it. The beam deflected every single time, in one direction or the other, with roughly equal frequency each way, exactly as a quantum gravitational field would produce, and exactly as the strict semiclassical equation forbids. That result is usually described as ruling out semiclassical gravity, and it is fair to say it wounded it badly. It is also fair to say that it leans on assumptions about how and when the quantum state collapses, and a determined defender of semiclassical gravity has ways to wriggle. It was strong evidence, rather than a clean kill. But it was the first time anybody had put a question this fundamental onto a bench and turned it into a measurement. 36 years later, two papers appeared, back to back, in the same issue of Physical Review Letters, in December of 2017, proposing something considerably sharper. One was by Sugato Bose and a long list of collaborators: Mazumdar, Morley, Ulbricht, Torosh, Paternostro, Geraci, Barker, Kim, and Milburn. The other was by Chiara Marletto and Vlatko Vedril. They had arrived at the same idea independently, and it is one of the most elegant experimental proposals in modern physics. Come with me and look at the apparatus, because it is small enough to picture completely. In a vacuum chamber, in the dark, two microscopic diamonds hang suspended, held in place, without touching anything. Each is a fraction of the width of a human hair. Each contains, at its heart, a single deliberate defect in the carbon lattice, a nitrogen vacancy center, a spot where one carbon atom has been replaced by nitrogen and its neighbor is missing. That defect has a spin, and the spin can be manipulated with light and with magnetic fields. Now the crucial step. A magnetic field gradient is applied, and because the spin of the defect can be in two states at once, and because the field pushes the two states in different directions, the entire diamond, millions upon millions of carbon atoms, is drawn into a superposition. It is in two places at the same time, separated by perhaps 100 micrometers. Then the same thing is done to the second diamond, a short distance away. And then everything else is switched off. No electromagnetic coupling between them, no contact. Nothing passing between the two diamonds except their own weight. They are left like that for a few seconds. Then the experimenters bring each diamond's two paths back together and ask a single question of the two spins. Are they entangled? If they are, the argument that follows is short, and it is the reason this proposal matters. There is a theorem in quantum information theory, older than this application by decades, usually referred to by the acronym LOCT, Local Operations and Classical Communication. It says that if two systems are separated, and the only thing passing between them is classical information, then no amount of local manipulation can create entanglement between them. Entanglement cannot be made classically. It has to be carried by something quantum. So, two masses, isolated, with nothing between them but gravity. If they come out entangled, then gravity carried it. And if gravity carried it, gravity is not a classical channel. That is a yes or no answer to the question this entire subject has been circling for a century, obtained on a table, in a room, with no accelerators, no neutron stars, and no Planck scale anything. It has not been done. I want to be as plain about that as I have been about everything else tonight, because this is exactly the kind of proposal that gets reported as though it has already happened. It has not. The proposal is 9 years old, and the experiment remains out of reach, and it is worth understanding precisely why, because the reason is a number we have met twice already. The masses required are around 10 to the minus 14 kilograms. That sounds tiny, and by everyday standards it is. A speck you could not see. By the standards of quantum superposition, It is gigantic. The largest objects ever put into a spatial superposition are molecules with a few thousand atoms. These diamonds contain something like 100 billion. The gap is many orders of magnitude. The separation required is around 100 micrometers, roughly the width of a human hair. Matter wave interferometry with large molecules works at separations hundreds of times smaller than that. The coherence time required is of order a second. Superpositions of large objects survive for tiny fractions of a second at best, because any interaction with the outside world, a stray gas molecule, a photon of thermal radiation, a vibration through the mount, destroys the superposition immediately. And every one of those three requirements has to be met simultaneously, in the same apparatus. Then there is the problem that comes from gravity's weakness, which is where our number returns for the third and last time. 10 to the 36. At a separation of 100 micrometers, the gravitational attraction between the two diamonds is not merely small, it is swamped by every other force in the neighborhood. Residual electric charge, fluctuating electric dipoles. The Casimir force between nearby surfaces, which is a real and measured effect, and which at these distances is comfortably larger than the gravitational one. To run the experiment, you have to shield or subtract all of those to a precision that leaves the gravitational effect standing alone, and that is the practical heart of the difficulty. The same weakness that made the graviton undetectable in Part 9 is here again, in a different costume, standing in the way of the one experiment that could bypass the graviton entirely. This is why the last several years of work on the idea have been about geometry and amplification rather than about running it. Papers on the optimal shapes for the test masses, so that the gravitational coupling is maximized relative to the electromagnetic contamination. Schemes for amplifying a weak entanglement signal into something measurable. Analyses of alternative platforms, optomechanical systems, harmonically trapped masses, clock interferometry. And alongside that, the theoretical argument has not stood still either, which is the part that most coverage leaves out. Several groups have examined whether entanglement generation really does prove quantumness as cleanly as the original papers suggested. Work published in 2025 looked at classes of semi-classical models, theories where gravity enters as a classical potential in the Schrödinger equation, and confirmed that they indeed fail to generate entanglement, which is the expected and reassuring result. Others have pushed the other way, arguing that entanglement generation on its own does not strictly establish that the mediating field is quantized, and that additional assumptions are doing work in the inference. So the situation as of tonight is this. The experiment has not been performed. It may be a decade away, or two, or it may not be achievable at all with any technology we can currently imagine. The theoretical interpretation is contested at the margins, though not at the center, and it remains, for all of that, the first proposal in the history of the subject that could give a real answer about the quantum nature of gravity without requiring energies 15 orders of magnitude beyond anything we can produce. And it is worth asking what happens if it runs, and the answer is no. Most coverage assumes a positive result and stops there, but the negative branch is arguably the more interesting one. If two masses are held in superposition with nothing between them but their own weight, and they emerge stubbornly unentangled, then one of the pillars of modern physics has moved. Either gravity really is a classical field responding to averages, in which case the graviton does not exist, and quantum mechanics has a boundary nobody expected, or the superpositions quietly collapsed on their own before the gravitational interaction had time to act, which is what several proposed modifications of quantum theory predict, and which would be an equally large result in the opposite direction. There is no outcome of this experiment that leaves the textbooks unchanged, which is the mark of a good one. For 100 years, the answer to whether gravity is quantum has lived at the Planck scale, unreachable, unfundable, permanently theoretical. It might instead live in 2 grains of diamond, a hair's width apart, in the dark, for 1 second. Which leaves us with only one thing left to do. We have to answer the question we started with. Part 13. What gravity is made of. So, what is gravity made of? I am not going to hedge it, because we have earned the answer. As far as quantum physics can currently say, gravity is made of gravitons. Massless, spin 2, 2 polarization states, coupled to everything that carries energy, with exactly the same strength, always attracting and never pushing. They are the quanta of the metric field, the granularity of the shape of space-time itself, in the same way that photons are the granularity of the electromagnetic field. That is the answer. It is the same sentence I gave you at the very beginning of tonight, before you knew what any of its words were carrying. But listen to what it sounds like now. It is exact where you live. The effective field theory built on gravitons describes the gravity of this room, this planet, the moon's orbit, and the collision of black holes a billion light-years away, and it does so with real quantum corrections that carry a coefficient of 41 over 10 pi and no adjustable parameters at all. That is not a sketch. It is a working quantum theory of gravity, and it has been sitting in the literature since 1994. It is silent where it matters. Those corrections are around 10 to the minus 70 at everyday separations, 57 orders of magnitude below the most precise measurement humanity has ever made, and the theory that produces them expires entirely at the Planck energy, 15 orders of magnitude beyond the largest machine we have ever built, and beyond any machine we could build. It has never been seen, and probably never will be. A Jupiter mass detector, at perfect efficiency, in orbit around a neutron star, would wait longer than the universe has existed, and the shield it would need to see through the neutrino background would collapse into a black hole before it protected anything. There may be a way around this. The 2024 proposal for watching a cooled crystal jump one rung up its energy ladder is real and serious, and has not been done. But the wall is structural, not technological. And it may not be fundamental. String theory says the graviton is one vibration of a closed string, and cannot be removed from any such theory. Loop quantum gravity says there is no graviton at the bottom at all, only nodes carrying volume, and links carrying area, with a smallest possible patch of space on the order of 10 to the minus 70 square meters. Causal set theory says there are only events and their ordering. The holographic program says gravity is made of correlations. 4 frameworks, and they do not disagree about the details of the answer. They disagree about whether the answer is the kind of thing that could be a particle. 4 qualifications, and every one of them is more interesting than the sentence they qualify. And notice that those 4 qualifications are not weaknesses in the answer. They are the answer's actual shape. Compare it to what you would have got if you had asked the same question about light in 1925. Light is made of photons, exact at every energy anyone has reached, audible in every laboratory, detected one at a time routinely, and fundamental as far as anyone can tell. 4 clean statements. No qualifications. Gravity gives you the same sentence with all 4 inverted. And that inversion is not a gap in our knowledge. It is a fact about gravity. It is what it is like to be the weakest force, coupled to everything, carried by something that carries itself. There is one more thing to say, and it is the deepest deflation available, and it is not a defeat. Ask what a sound wave is made of. The honest answer is that it is not made of anything, in the way that an object is made of something. It is a pattern in air. The air is made of molecules, and the wave is a particular way that those molecules are moving, a coordination, not a substance. And yet sound is quantized. The quantum of sound has a name, the phonon, and it is entirely real in every operational sense. It carries a definite energy, It scatters off things. It obeys conservation laws. Solid-state physicists calculate with phonons constantly and could not do their work without them. A phonon is real, and a phonon is not a substance, and there is no contradiction between those two statements. The graviton may be exactly this: a quantized excitation of a field, real, energetic, carrying momentum and spin, appearing in every honest calculation, and not a brick in a wall. In which case the answer to tonight's question is that gravity is made of gravitons in precisely the way that sound is made of phonons, which is a true and complete answer that also quietly changes what the word made was doing the whole time. And if that is the case, then the thing underneath the graviton is not a smaller particle. It is whatever plays the role that the air plays for sound: strings, or a spin network, or a set of ordered events, or a web of entanglement. The graviton would be the ripple, and the ripple is never the thing that ripples. Which brings us back to where we started, and to something I told you near the beginning of tonight. You have never felt gravity. When we first said that, it was a trick of framing, a way of noticing that the sensation you call weight is a chair pushing electromagnetically against you, and that in free fall, the instrument reads 0, and so do you. It was a good line, and it was mostly a curiosity. Hear it again now, with everything in between. You have never felt gravity, because there may be nothing there to feel, not a force pulling on you. A shape, described by a field, whose ripples come in quanta, we can specify completely, and will very likely never hold, and which may themselves be the collective behavior of something we have not identified, in a theory nobody has yet written. You spend every second of your life inside this. It holds your feet to the floor. It holds the ocean to the planet. It built every star you have ever seen, and it will decide how the universe ends. And when you ask what it is made of, physics can hand you a name, a complete specification, a working calculation, and an argument that you will never be permitted to see one. That is not a failure. That is a very specific and very unusual kind of knowledge. We are in the position of someone who can describe a room in perfect detail through a wall they will never be able to walk through. The question was never whether gravity is made of something. The question was whether made of is a phrase that survives contact with a thing that is not a substance, not a force, and possibly not a particle. And the honest answer, tonight, in 2026, is that we have a name for the thing holding the universe together. We know almost everything theory can tell us about it, and we may never be allowed to look. Somewhere out there, two black holes are finishing a spiral that started before the Earth existed. The ripple is on its way. It will arrive here carrying something like 10 to the 78 quanta of a field whose nature is still an open question. It will stretch this planet by less than the width of a proton, and it will pass through you without your noticing, the way it has done every day of your life. And whatever it is made of, it is still going. It was going long before anyone thought to ask the question, and it will still be going long after the last person who cared about the answer has stopped asking it.